My name is Nikola Banovic. My research focuses on creating technology that can help people improve the quality of their lives by making them more productive, healthy, and safe. And in my work, I leverage computational modeling and AI to create this kind of technology. So in this talk today, I will actually give you two examples of the technology that I created. One is the driver coach that can automatically detect when somebody's driving aggressively and then coach them how to be safer in traffic. And the other example is going to be behavior dashboard, which is a visual analytics tool that can help clinicians explore behaviors of their patients, understand different healthcare outcomes, such as, for example, rehospitalization, but also simulate different kinds of behavior-based interventions that can help improve those outcomes. Now, in human-computer interaction, the field that I'm part of, we try to understand how people interact with information technology, such as, for example, this desktop computer, and then use this knowledge to help improve the existing interfaces or inform the design of future interfaces. And for a very long time, modeling human behavior has been a very important tool in doing that. What modeling allows us to do is predict how people interact with various user interfaces, how quickly they can type or how quickly they can point at different targets. And this is not a new idea. We don't just go and create an airplane wing, put it on an airplane, and fly it to test it. We actually create a computational model, a mathematical representation of that wing. And then we simulate different environments in which this wing will find itself, and then predict how it will behave so that we find the perfect wing that we can later on build, deploy, and test. And the same thing I want to do with user interfaces. I want to be able to simulate the environments in which people find themselves in, and then predict their interaction with interfaces to evaluate them before empirical studies. And this kind of computational modeling has had a lot of success in many fields. Poster child definitely is climate modeling, where we have these models that evolved from early 70s to today to these very complex simulations of ecological systems that require supercomputers to run. And despite these kinds of success stories and the computational powers that we have today, in HCI we still use mostly very simple regression to model human behavior. The challenge is that that is no longer working because the technology is evolving, and what we used to simulate as a very simple interaction with a desktop computer in an office is now changing to multiple devices in environments that look nothing like offices, and the kinds of behaviors and interactions that look nothing like office work. But at the same time, these kinds of technologies enable us to sense, collect, and store data about people's behaviors at a massive scale, allowing us to study almost any aspect of people's lives, from their daily routines, their exercising routines, how they interact with different interfaces, even tasks that you wouldn't necessarily think of as HCI problems, such as driving, that I will talk about a little bit later. And this kind of data is now stored in these massive behavior logs that contain a lot of heterogeneous, multivariate, often unlabeled data, which means that the existing techniques to manually explore it using very simple visualization or exploratory data analysis are very tedious. And on the other hand, if we're not very careful, the automated data mining techniques might extract patterns from the data that don't necessarily match behaviors of people, but just some patterns based on spurious correlations in the data. So in my work, I'm very careful how I model people's behaviors as sequences of situations that people find themselves in and the actions that they perform in those situations, to then build probabilistic models that capture the inherent uncertainty in people's behavior. And I do that by leveraging AI-based techniques, such as inverse reinforcement learning, that has traditionally been used to train robots by demonstration. But the insight here is, well, if we can train robots by human demonstration, then we can use the same technique to capture demonstrated or enacted human behaviors. And then, having these kinds of models, we can start building technology that can automatically describe, reason about, and act in response to people's behaviors. So one such example is driver coach, that can automatically detect when somebody is driving aggressively, in this particular case, the transparent vehicle that is speeding through the intersection, and then simulate what non-aggressive driver would do in the same situation, the opaque vehicle that is keeping sort of within the speed limit. Even if we don't have any examples of non-aggressive drivers driving through this particular intersection that I'm showing you here. Now, this problem is important because aggressive driving is one of the leading causes of fatal collisions, both in the US and worldwide. And if we're able to raise awareness of aggressive drivers' behaviors, let's say even just those drivers who are court-ordered to take rehabilitation driving courses, then perhaps we can make them and others safer in traffic. So we tested the ability of our driver coach to do this, to raise people's awareness. So we ran a user study, and we recruited 20 participants. We asked them to fill out a questionnaire that subjectively rates their aggressive behaviors in very specific situations, such as, for example, speeding through an intersection, running through yellow light. And then we asked them to drive through a specified set of intersections on city streets. We collected their naturalistic driving data and then loaded it into our tool. Now, the tool was able to leverage aggressive and non-aggressive driving computational models of behavior to then automatically process this data and show it in two different conditions. In the baseline, we would just simulate behavior, we would just show the behaviors that drivers exhibited. We did not have any intervention to tell them this is aggressive or non-aggressive driving behavior, and there was no way to simulate this kind of behavior. And in the other test group, we gave them the full functioning driver coach. We only showed them the aggressive behaviors that they performed, and then also allowed them to simulate non-aggressive behaviors to contrast them with what they have done. And then we asked them again to fill out the same questionnaire. And what we were able to find was that drivers in the test group were more likely to raise their scores for aggressive driving for very specific instances that we were able to identify in their driving compared to the pretest than compared to the other baseline group. And this shows us some evidence that these kinds of technologies can perhaps just do enough to raise people's awareness about their poor driving behaviors and later on help them improve. Now, the driver coach is an example of a technology that targets very specific stakeholder group for a very specific behavior. But in my work, I'm also interested in creating technology that can help domain experts across different domains explore people's behaviors. And an example that I will show you today is how we can leverage the behavior dashboard, the visual analytics tool that I created, in a specific case where clinicians are interested in understanding the behaviors of patients who have undergone a pancreatic surgery. Most of these patients are pancreatic cancer patients. And the motivation for the work was the insight from the clinicians that there's some kind of a correlation between people's physical activity and their rehospitalization following the surgery, where they're hypothesizing that if a patient walks more, there's a lower chance of rehospitalization. And for patients who walk less and have long sedentary behaviors, they're more likely to be rehospitalized. So we started with this idea and recruited over 50 patients from this stakeholder group, and then collected their data about whether they were rehospitalized or not within 30 days, their demographic data such as gender, age, the stage that they were in the process, whether they were hospitalized in the hospital at the moment or not, and then also subjective ratings of their pain and nausea symptoms, and objective measures of their activity collected from fitness trackers and their mobile devices. Now, I'm not going to get into too much detail about the ability of these kinds of models to predict rehospitalization. We were as good as some of the clinical baselines, and in terms of recall, even exceeded their precision. But I just want to show you very quickly how simulation and prediction, these components of computational modeling, can help us here. So what I can do is I can actually query the model now and say, show me the behaviors of these patients on the day that they were discharged. And when I specify that, what I can do is I can start simulating from that particular point in time. So I can say, well, simulate the behavior for the next 60 days. And what that allows me to do is to look at these sequences of situations and actions and understand how does their readmission rate change over time depending on the situations that they find themselves in, for example, their symptoms, and the actions that they perform, whether they choose to walk or not. And then what we're able to do is to look at different time stamps, 10 days, 30 days, 90 days, and see that the probability of somebody being rehospitalized increases. Now I can do a similar thing and simulate what would happen if a patient walks more. And sure enough, the model predicts that this patient is going to be less likely to be readmitted. But what we also found was that patients who have low pain and low nausea, they're able to walk more, they're not rehospitalized. Patients who have high pain, high nausea, they're unable to walk, and thus they're also rehospitalized. And these kinds of findings, this ability to simulate and predict behavior before we even create these potentially expensive interventions that can affect patients' well-being, helped us understand that we need a more holistic approach to this problem than just prompting people, walk more, walk more, walk more. So these are just two very simple examples of how AI enables us to study human behaviors at scale and create user interfaces that can automatically reason about people's behaviors and then act in response to those behaviors to enable technology that will improve the quality of people's lives. Thank you.